So it's my great pleasure to introduce Bernhard Schölkopf. And it's really easy to introduce him because he's famous for so many things. He's a director at the Max Planck Institute for Intelligent Systems in Tübingen. And he's probably most famous for developing support vector machines and more generally leading the kernel revolution of the early 2000s. And for those of you who are perhaps so new to the field, you might not even know that kernels were sort of the last big wave of excitement before deep learning. Recently, Bernhard has started doing more foundational work on causality, which I'm excited to hear about. So please take it away, Bernhard.
Thank you very much for the introduction. Thank you very much for the invitation. It's great to be here. Thanks for coming to my talk. So I'll talk about work done at the Max Planck Institute for Intelligent Systems. I should add that I'm currently at Amazon, so it was actually a very easy drive by car up from Seattle. So it's one of the first conference talks without jet lag here. And I'll be talking about causality. So dependence versus causation is a big historical issue in philosophy of science and science in general. And I'll start with an example, which is the example of storks and human birth rates. So there's a strong correlation between the number of storks, for instance, in this case living in Germany, and the human birth rate. So given the number of storks, we can predict the human birth rate with relatively high accuracy, actually in this case even using a linear model. So for every, roughly speaking, for every pair of brooding storks, we have about 500 new babies per year. So if Angela Merkel calls Donald Trump, she could tell him that number, and Trump could use it for prediction in the US potentially. Now, how should Angela communicate the model to Donald in a way that he will be able to understand? And it turns out, although this is maybe the simplest possible model imaginable, it's a non-trivial model how to communicate this. So we can't simply say that each pair of storks brings 500 babies per year. The model is only valid in a certain IID setting, which I hope will become clear during the talk. And chances are he won't understand this IID setting. And maybe he isn't interested in prediction anyway. Maybe he's more interested in intervention. And so suppose he wants to have more babies in the US. Should he change the number of storks or not? And this, of course, leads us to the relationship between dependence and causality. And this is something that maybe was first understood by this philosopher and physicist, Hans Reichenbach. He postulated something he called the common cause principle. And this principle says if you find two observables, x and y, to be statistically dependent, then there exists another variable, let's call it z, that causally influences both of them. And this variable explains all the dependence between x and y in the sense that if we conditioned on z, x and y become independent. And as a special case, this variable could coincide with x or y, in which case we get these graphs, but in the generic case we would have this kind of graph. Now, if the storks bring the babies, then the green graph would be the correct one. If the babies attract storks, it's this graph, and if there's some other variable, such as economic development, that causes both of them, then the red one is correct. Now, the crucial insight is that without making any additional assumptions, we cannot distinguish these three cases based on observational data. So the class of observational distributions over x and y that we can realize by these models is the same in all three cases. So a causal model, and these are three different causal models, obviously, a causal model contains genuinely more information than a statistical one. Now, this connection between causality and statistics was further elaborated and refined and built into a beautiful theory by Pearl and others. So this is a picture of Judea Pearl. And in this theory, in the simplest case, we assume that we have a set of observables or variables that form the vertices of a direct acyclic graph. In this graph, arrows represent direct causation. And in the graph, moreover, we assume that at each node we have a function which gives us the value of that observable or variable depending on the values of the parents in the graph. So PA stands for the parent, so these are the outputs of the parent nodes, and a noise variable. Actually, the shorthand here is a U, so actually it's what people call an unexplained variable. We often think of it as a noise, but it could be something else. So we have an unexplained variable at each node. So that gives us a set of such variables. And to make the whole thing statistical, we could specify a joint factorizing distribution over these variables. So we assume these random variables are joint, these noise variables are jointly independent, and we call them UI. Now, everything is deterministic apart from these noises that we feed in here. And of course, once we specify a joint distribution, a factorizing joint distribution over these noises, we get an overall distribution of all observables. That's called the observational distribution. And it turns out this distribution has an interesting property, which it inherits from the graph structure, from the topology of this graph. And this property is characterized by the causal Markov condition, which says that whenever we condition, so let's sit on this node here, the green one, whenever we condition on the parents of these nodes, this random variable becomes independent of its non-descendants. So these are the descendants. Everything else is a non-descendant, except if it's a parent. So this becomes independent of its non-descendants when conditioned on the parents. And this graph, together with the joint distribution, are also called a graphical model. Now, interestingly, this property is a kind of a footprint of the topology of the graph that we can pick up in the joint distribution in terms of conditional independence properties. So in a way, you can think of this as follows. You have a noise probe that you feed in at each node, the independent noises, and now you start asking conditional questions, or you test for conditional properties of the form, what does this node know about this one that it doesn't know from this one, etc. So if you ask all these questions, then you learn something about the graph topology. And you can ask these questions if you have a functional conditional independence test, which is a hard problem in its own right. But in principle, you could do that. But you can only do it if you have at least 3 nodes, because if you have 2, there's no conditional independence test or property to be tested. It's a ternary relationship. You need A, B, and C. So in the 2-variable case, there's nothing you could do. So this was a problem that we've focused on for quite a while. And actually, it led us to some interesting insights that also have implications for the case of more than 2 variables, and that, as I will try to convince you today, also has implications for machine learning. And so the 2-variable problem is, of course, a classic problem. This is an old philosopher, Nietzsche, who talked about this in this book here. So the first chapter, the 4 great errors, starts with the biggest of them all, the error of mistaking cause for consequence, which he calls reason's intrinsic form of corruption. So can we tell cause from consequence? And I want to introduce sort of one idea, which will be elaborated in this talk, and I'll introduce it with this simple example here to give you some intuition. So we have an example of 2 variables, altitude and temperature. So this is temperature readings, average annual temperature from a number of weather stations in Germany. And you can see that the higher it gets, the colder it gets. So this is in Celsius, this is in meters. You can see that most places are relatively low. And now you could ask the question, does temperature cause altitude, or does altitude cause temperature? And of course, with all causal questions, it's quite subtle to really decide, and you can question anything. But I think most people would say, I think it's reasonable to believe that altitude has a causal effect on temperature. And most people would say, I don't believe that temperature directly has a causal effect on altitude. So from that point of view, we would think it's reasonable to consider altitude as the input in our causal model and to factorize the joint distribution in this way. So we first sort of choose an altitude, and then there is some mechanism that, given the altitude, somehow converts this into a distribution over plausible temperatures. So suppose you don't believe me and I have to convince you somehow. There are multiple ways I could try to convince you. So the first one is the most expensive one. I could try to make an intervention experiment. So I could build a big machinery to lift the city of Vancouver by 1 kilometer, and then we'll continue measuring the temperature, and next year we find that it's actually a little bit colder than this year. So that would be a possible way to go, but obviously you can't always intervene. There are actually many, many cases where you can't intervene for ethical reasons, for mechanical reasons, or for whatever reasons. So really, we want other means of doing inference. Now, sometimes it's enough to just do a thought experiment, do a hypothetical intervention. So I could tell you, well, look, let's imagine we built this apparatus to lift the city of Vancouver, and since we've both taken some high school physics, maybe we will agree that if we go up, the air pressure will go down, and maybe when the air pressure goes down, I don't know, there's less atmosphere around to keep the Earth from cooling into space or whatever. I don't want to speculate on the exact mechanisms, but I think I could probably convince you somehow that it would be plausible that the altitude, the change of altitude will have a causal effect on the temperature. So if I convince you of this, then I would probably talk about physics, talk about physical mechanisms that, given the altitude, plausibly argue that the temperature will change. So it's really an argument that implicitly assumes an independence between the physical mechanisms and the input distribution. So that's the second point. First one is intervention, second one is a certain type of independence. And actually this independence is also related to a notion of invariance, which could be used as follows. So I could, for instance, say, well, suppose I can get another data set. Let's say I have two data sets of somewhat comparable countries. Let's say I take Austria and Switzerland. The data sets look a little bit different, but then I find out I can fit these two data sets using the same conditional, so using an invariant conditional. Maybe that would also plausibly argue that this thing, since it applies both in Austria and Switzerland, this is a property of physics, whereas the other one, the distribution of altitudes, maybe that's a sort of culturally contingent. Maybe the Austrians like to build their cities higher than the Swiss or something like that. So these are three different ideas, and I think they also can be illustrated, or the underlying notion of independence can be illustrated also with this example here, which is a so-called Bechet chair. And whenever we see some object, our brain makes the assumption that the object and the mechanism by which the light reaches our brain are independent. Now, we can violate this assumption by looking at the object from a very specific point, and in this case, we can look through this little hole, and if we do that, perception fails because we see a 3D structure which in reality isn't there. Now, in the independence assumption that our visual system makes is a good one because most of the time it holds. So we assume, our brain assumes that the objects are independent of the vantage point, they're independent of the illumination, and this rules out any sorts of accidental coincidences or 3D structures that line up in 2D, etc. And that's what's called the generic viewpoint assumption in vision. And of course, also if I move around an object, my vantage point changes, but I assume that the object itself is unaffected by my change of vantage point. And that's an invariance, which is implied by this independence, and it allows me to do something which in vision is called structure for motion. So I can close one eye, move my head around an object, and still get 3D information for that. And that only works because I'm assuming that the object doesn't change. So let's assume we have a causal generative process which is composed of autonomous modules that do not inform or influence each other. So every causal graph implies a corresponding factorization of the joint distribution. And I've written down such a factorization here in terms of the parents in the graph, and let's assume these are the causal parents. And this factorization is one into which I assume that this will be into independent conditionals, and those we will call the causal mechanisms. Now, I will generically assume or argue that every change in the real-world distribution that we see out there always has to come from a change in causal conditionals, or in other words, structural functions, structural assignments, or structural equations, depending which terminology you like, and noise variables. So always something like this has to change. In the generic case, not all of them have to change, because if we change one of them, it doesn't automatically imply a change of another one. They're independent objects. Now, this locality of change doesn't apply if we factorize according to some other graph. So if we factorize according to a graph which does not capture the correct causal structure, then in the generic case, it turns out that changing one thing will sort of have to be counterbalanced by changing other things at the same time. Now, here's a kind of a special case of this, which is something that Irscha said last year before NIPS in a talk, which I found intriguing. He called this the abstraction challenge for unsupervised learning. And the question that he posed is, why is it so much worse to model directly the density of acoustics, so the acoustic signal, compared to modeling separately the condition of acoustics given phonemes times the density of phonemes? And I think one explanation from the point of view of causality is that this second formulation is a decomposition into causal conditionals. So no matter what phonemes I want to produce, I will use approximately the same red conditional. So this is an invariant property, so it will be the same for many different tasks or data sets. So in that sense, it should be easier to learn from different tasks and data sets. So I haven't yet told you what I really mean by independence of mechanisms. And this, of course, this has to be formalized, and there are different formalizations. I'll give you two of them. The first one is a statistical one. The second one will be something in terms of algorithmic complexity. The first one looks at the special case of having only two variables and no noise. So in this case, the conditional is just a function, and this function should be independent of the input distribution, which is shown down here. So if this independence holds true still informally, then we would expect to see a dependence between the function and the output distribution, because we would expect that wherever this function is flat, the output density tends to have large values. Slightly more formally, we will postulate that the covariance between the input density and the derivative of the function, in fact, the log of the derivative for some technical reasons, should be 0. So you'll see that here in this case, there's a positive correlation between the density value and the derivative of the inverse function. So we will assume that in the case of independence in the forward direction, in the causal direction, covariance between these two quantities should vanish. Of course, for this covariance to make sense, we have to specify what we mean by this. So we have to define a probability space on which these two things are random variables. We will just use the probability, the 0-1 interval and Lebesgue measure, and then we can formally define that. And moreover, we can then prove that unless the function is the identity, in the backward direction, the same kind of independence measure will be strictly non-zero. So if we have independence in the forward direction, we provably have non-independent, or we have dependence in the backward direction. So we have an asymmetry suddenly between cause and effect, which is implied by assuming independence of the input in the mechanism, which is a special case, just a two-variable special case of the general concept of independent mechanisms. Now the input, because the input is just a distribution, it's just the preparation of the input distribution, if you want, can be identified with the mechanism. Okay, so this kind of thing can be sort of written down, or it leads to sort of estimators that you can actually try on data, and we have a set of data sets, and it turns out that if you apply this kind of method, and there's a whole set of different causality inference methods now, then you can do a reasonable job as telling cause from effect, which people previously thought is impossible. So you can roughly do 75% correct, sometimes more. So far, I've talked about links between causal structure and statistical structure, but actually the causal structure is the fundamental one, because it captures the physical mechanisms that generate statistical dependence in the first place. So the statistical structure, from my point of view, is actually just an epiphenomenon that follows if we make you assume a causal model, you have some unexplained variables, and then you make the unexplained variables random, and this implies a joint distribution that has certain statistical properties. But it doesn't have to be like that, and you can instead make the unexplained variables random bit strings, which we've done in this case. So here we have a DAG which has a computer program, UJ, sitting on each node, and they run on Turing machine T. They take as inputs the results of the parents, and we assume that all programs are jointly independent. All these things are jointly independent in the sense of Kolmogorov complexity, so that means a joint compression of these bit strings does not save space compared to individual compressions. So if we are willing to make these assumptions, then we can prove that this model, so this is like a structured equation model, like a functional causal model, it implies a causal Markov condition, just like in the statistical case. So that's interesting because you get something like a theory for graphical models, which is analogous to the statistical case, but it's in terms of Markov complexity. So this is an interesting other form of independence or other formalization of independence, and it has some interesting implications, I think, for physics. And to see this, we look at this Gedanken experiment here. So in this experiment, we have a beam of particles that comes in. So this is our cause, if you want. So we prepare this cause distribution. Or this cause state, and then this cause gets transformed by a conditional, or it gets scattered at an object. So this is the mechanism. And then the outgoing beam, so these arrows that go out in different directions, that's the effect, obviously contains information about the object. That's what makes vision possible, or that's what makes photography possible. Photons contain information about the object where they have been scattered. Now, we all know that microscopically, from the point of view of physics, the time evolution is reversible. So things should be symmetric microscopically. Nevertheless, the photons contain information about the object only after the scattering, not before. So why is that the case? So why do photographs show the past rather than the future? And of course, this is due to our assumption of independence at the beginning, right? Because we're putting this in a sense, and then we automatically, it turns out we get out the thermodynamic error of time. So in this case, the independence assumption will read that, so we have some initial state of a physical system, we have the mechanism, which is just the system dynamics applied for some fixed time. It's an invertible mapping. And we will assume that the initial state and the mechanism are algorithmically independent in the sense of a mutual algorithmic complexity, and also algorithmically independent, and which means that knowing S does not enable a shorter description of M and vice versa. And if we do this, then we can actually prove that the Kolmogorov complexity is non-decreasing under this dynamics. So if we apply this mapping, our mechanism to the state, we end up with a Kolmogorov complexity which is lower bounded by the one initially, this plus. I think that's a detail. A Kolmogorov complexity is only ever defined up to an additive constant. So we can prove that this quantity does not decrease, can only increase. And in a way, that's the second law of thermodynamics, provided, so it gives us the thermodynamic error of time, provided you are willing to accept Kolmogorov complexity as a sensible measure of entropy, which is something that quite a few physicists working on fundamental problems have put forward. So I think that's an interesting connection. But I want to now come back to statistical implications of causal structures and talk about their impact on machine learning. So this is a topic that has gained some traction in recent years, and I'll try to discuss 2 or 3 of the applications that are listed here. I think all of them are related to the factorization of the joint distribution into independent conditionals or independent mechanisms. And just to remind you, so if we do this factorization according to the underlying causal graph, then we expect that these mechanisms will be independent. So if we use the wrong graph to factorize our distribution, because for each distribution many such factorizations are possible, if we use the wrong one, we would not expect that these objects are independent. So this point we've recently observed also in neural network models, and I thought that might be interesting for this community here. And to talk about that, I first want to distinguish between causal and anti-causal machine learning problems. So in machine learning, we always take X, or let's say supervised machine learning, we have some X, we try to predict Y. We usually don't care about the underlying causal structure, but there's many possibilities, and the 2 simplest ones is that X could be a cause of Y, or Y could be a cause of X. In the first case, let's call it a causal learning problem, and the second case, an anti-causal learning problem. Now, in some cases, such as in VAE models or encoder-decoder models, both directions occur in the same model, and it's interesting to look for independent mechanisms in such models. So to this end, we can use a dependence measure. We use a specific one that we developed looking for dependence in Fourier space. We developed this for time series signals and applied it with some success there. And now we've applied it to spatial convolutions. And we use it here now to measure the dependence of filters in successive layers of VAE ConvNet models. And when we do this, so this is work with Michel Bessel, we observe actually two interesting things. The first one is that if you look in the causal direction, so the generative direction, then you do find independence. So you find approximate independence between filters of successive layers, which means in our case that these blue distributions are roughly centered on the number 1. So we have the quantity that we measure is 1 for independence. And if we do the same thing in the anti-causal direction, so in the encoder, then we always see dependence, and it turns out that dependence increases as we get closer to the low-level features. So it starts, So that's interesting. We start with a relative dependence, and then as we get closer to the lower-level features, the dependence increases, so this orange curve moves further away from the number 1. So what this thing shows or illustrates is that the underlying causal direction does have an influence, or makes a difference for if you want, for the physics of machine learning, because the independent mechanism assumption, if you want, is a physical assumption. It's an assumption that may or may not hold true for real data, and it turns out it makes a difference. Now let's look at another example, which is my favorite implication of causal direction, and this is the implication for semi-supervised learning. So whenever we want to learn a mapping from X to Y, we want to estimate properties of the conditional. So if we do regression estimation, we estimate the conditional mean. If we do classification, maybe we estimate where this quantity passes through 0.5. And in semi-supervised learning, we try to improve this estimate by having additional data from P of X. Now, of course, this can only possibly help if there is a link or a dependence between P of X and P of Y given X. And now this makes you suspicious already. I told you before about my independence assumption. So if we go to the case of causal learning, we actually assume to begin with that these two objects are independent. Therefore, semi-supervised learning should be impossible. On the other hand, in the anti-causal setting, it's the other way around, because in the backward direction, we actually did, in this simple model from before, we got a strict dependence between these two objects. So in this case, in principle, semi-supervised learning could be possible. And one can make a similar argument for covariative transfer learning, and there it's kind of the other way around. But let's stick with semi-supervised learning. So we predict that in the causal direction, semi-supervised learning should be impossible. And this is what we very nicely found. And we didn't even have to run experiments for it. We just took benchmarks that other people had run. And then we label their data sets into causal, anti-causal, or confounded. Each such label and tells us what we would expect. Do we expect that they can improve things or not? And our meta-analysis of these benchmarks beautifully confirmed the prediction that in the causal direction, semi-supervised learning doesn't help. And it's also instructive to think about the different assumptions people have come up with to justify semi-supervised learning. Turns out they all can be viewed as linking the P of X and the conditional P of Y given X. So they all need some kind of link between these two objects. One example is the cluster assumption. But I'll move on to the next example. So this is an application example of how causality inspired the work in machine learning. And this is based on this data from the Kepler satellite, which is a space telescope that NASA launched in 2009. It's named after the astronomer Kepler, and it observed 150,000 stars in this direction here for 4 years. And in these observations, Kepler is looking for exoplanet transits. So these are events where a planet partially occludes the host star, because we look at it from the side of the solar system, and this causes a slight decrease in brightness, a very slight one usually, usually orders of magnitude smaller than the influence of instrument errors. Now we observe a set of such pixel light curves. Each of these pixels now, so this is a pixel on the CCD. Each point on these curves is typically a half-hour exposure. So the number of photons gathered by that pixel on the CCD in this half hour. And then we get these light curves. We see some of them get fainter, some of them get brighter. All of those actually belong to the same star. So the star sort of slightly shifts around on the CCD, even though the telescope even tries to correct for changes in solar radiation pressure. But in the end, we are interested in this signal here, which is the signal that comes from the star, but we only observe this one here, which is affected both by the star and by the instrument errors. So we'd like to reconstruct Q. It seems to be hard, since we don't know the instrument error, but we are measuring 150,000 stars, so we are measuring many other stars at the same time. And there's two aspects of these other stars that are important. First of all, they have no causal link to the signal that we are measuring, and they're measured by the same instrument. So the other stars actually, as we measure them, are half siblings of our star. So we've developed an inference method that removes the effect of the instrument. And the method, we have a nice result, a theoretical, or several theoretical results. So we can prove that it recovers this random variable almost surely up to a constant offset, subject to two assumptions. The first one is that our observed quantity is the sum of Q and some function of the noise. We don't need to know that function. And the second assumption is that all the information about that function of the noise that gets added to this thing is present somewhere in the other measurements. We don't need to know where it is, but in principle, the effect of the noise should be some function of the other measurements. Now, if we combine this method, which in the end is just like a regression method, if we combine this method with efficient methods for searching light curves, we actually get a nice method for finding exoplanets, and we've discovered about 15 new exoplanets. So I'm going to skip through this work, which I didn't expect to get through. This is something, some causal method for fairness, and instead briefly talk about this thing here, which is a method to learn independent mechanism using neural network models. So here we assume that we have a data set which has been transformed by a number of different and unknown transformations, and we try to recover these different factors of variation without supervision. So the data are handwritten digits. The transformations are things like adding noise, contrast inversion, or translations. And what we're going to do is we learn to invert these mechanisms with this architecture, which combines competition between a set of experts and something like a GAN. So when a transformed digit comes in here, all these different experts, they try their luck. So these experts try to invert this transformation. Each of them tries their luck. They produce some output. The discriminator then tells us which one looks most like an MNIST digit. And then the one that wins gets trained to increase the score measured by the discriminator. And the discriminator at the same time is trained all the time, trained to distinguish transformed digits from real digits. Now, suppose the transformations that we want to invert are independent to begin with, in the sense that they should not contain information about each other. So this is slightly informal. There are ways to make it more formal. But suppose they are independent, and by which we mean, in a sense, that performing well at one of the tasks of one expert should not improve performance on another. So they're sort of going in different directions. The space learning one doesn't help you with another one. And then this is exactly what allows the experts to specialize, because if one of them gets better at one task, it doesn't give this expert any advantage in specializing into the other tasks. So the other experts can specialize in the other tasks, and we initialize all of them to the identity. And so in this sense, this competitive training procedure is exactly what exploits the assumption of independent causal mechanisms. And if we do this, so here every plot is a mechanism to be learned, so left translation, down translation, etc. Each color is an expert. So this, for instance, this green graph shows that this shows the discriminator value that the green expert achieves on this task of left translation. So you can see that it eventually specializes to invert this thing. If you look at the red one, the red expert initially cannot decide between these two tasks. At some point, it decides to specialize on this one, and then this task up here gets taken over by the green expert. And in the end, they all have converged. And yeah, so this is worked out nicely and worked quite robustly. And then afterwards, once the system is trained, you take random inputs that have been transformed by one of the mechanisms, and then this is the output of the winning expert. And we can quantify how this helps by this experiment where we feed the transformed digits to a standard MNIST classifier. So if you took this just a standard MNIST classifier trained on the original digits, if you feed it with transformed digits, you get an error rate of 40%. The original error rate is close to 100%. Now, if we pre-process our digits with our model, we get performance which is actually close to the optimum here after relatively short training. So if we train our model only 200 iterations, each iteration being a mini batch of 32 examples, so this is just 6,000 examples, we already get quite a respectable performance here. And this is if the number of experts is too many or too few, you still get reasonable results. If you have too many experts, some of them don't specialize. If you have too few, some of them specialize on multiple transformations at the same time. And my favorite example here is that we can also nicely generalize to other classes of inputs. So the experts trained on MNIST, afterwards we can apply them, for instance, to these omniglot characters and each expert. So this is the contrast inversion expert. These are the translation experts. Each expert does something reasonable. Okay, so I'm coming to the end. Last 3 slides, I think. The long-term goal of this kind of work, or my long-term goal, is that I would like to learn structural causal models from a multitude of tasks in multiple environments. So in a way, sort of a brain that can do many things, not just one. So I think these models need to reuse components, which would require that the components are robust across tasks. And I think a sensible inductive bias for this is to look for independent causal mechanisms. And maybe competitive training can play a role in this. Now, the overall problem, of course, is closely related to something people have started to call disentanglement. And I have to admit, I sort of find that problem not very well defined. I don't quite understand it. And maybe one could make sense of it in terms of causality, but I also don't have a good answer for that yet. We have a paper on a slightly more principled way of doing disentanglement, which is the workshop session, so please check it out. Overall, I think we have, as a field, especially this community here, have made a lot of progress in representation learning. And usually that refers to the representation of a fixed probability distribution. So it's kind of an IID setting, and we want to represent an IID distribution. But our brains really need to represent causal models. And causal models, they capture not just one distribution, but a whole set of distributions, interventional distributions. And I think that's totally open how we should represent those. And it probably has to do with RL, with causality, with planning and reasoning. And if you want, you could say it has to do with everything that's related to thinking, which we're not very good at yet. So I think I'm going to skip, so maybe just mention that I think a beautiful way to think about thinking is what the ethologist Konrad Lorenz said. For him, thinking is actually nothing but acting in an imagined space. So we need to learn models in which we can act in an imagined space. And these won't be statistical. I think these won't be purely statistical models. They also won't be super complicated differential equation models. I think we need a level of complexity in between. And I think causality might play a role here. So as we've heard this morning, the first industrial revolution was triggered by the steam engine. The second one was mainly driven by electrification. If we think about it broadly, both of them are about how to generate and convert forms of energy. And we should delete the word generate, because energy, as we know, is a conserved quantity. So we're currently experiencing another revolution, which I think actually already started. It's not so current. I think it started in the mid-20th century under the name of cybernetics. And it replaced, the most interesting thing about it is that it replaced energy by information. Now, just like energy, as we heard this morning, information can also be processed by people, but to do it at an industrial scale, we need computers, and maybe to do it intelligently, we need machine learning and AI. Now, the analogy goes further. Just like energy, information is probably a conserved quantity in physics, so we can only convert and process it. I don't know, one can speculate about this analogy a bit more. So with energy, it took a long time, maybe until Emmy Noether in the early 20th century, to really understand it as a constant of motion related to certain symmetries or covariances. And we might be at a similar stage now with respect to information. So we know how to extract some of it. We have relatively crude methods, and maybe one could also say we are currently a little bit intoxicated by the success of these methods. I don't know, maybe a bit like people must have been amazed with what could be done using steam engines, but probably we don't fully understand it yet, and I think that may have to do with causality. So causality tells us that statistical information is just an epiphenomenon, and dependencies come from underlying causal structures. So with that, I would like to thank all my co-workers, and thank you for your attention.
Thank you, Bernhard. Okay, we have time for one question. And can the next speaker come up here? Wow, no questions. It's your big chance. Okay, then I'll ask a question. You were talking earlier about time reversibility. When we have time series data and say like a hidden Markov model, how much work is done for free for us by encoding the time stamps of the data?
Yeah, so time gives us constraints. We know that the future can't cause the past, so certain causal connections are ruled out by time, but in a way it's only a small part of the problem. So not everything that when X happens before Y, it doesn't imply that X causes Y, and the problem of confounding is just as hard as it is in the case where you don't talk about time. So in a way, it's interesting that one can talk about causality without talking about time, and that's a whole discussion in its own right, and maybe I shouldn't start that now, but I think it's a very interesting problem.
All right, let's thank Bernhard.